So we'll start off with examining the principles of isokinetic dynamometry, and we'll do that from a perspective of starting with what it is and then getting into an understanding of how we set the dynamometer up and what the dynamometer is recording. So we'll take this paragraph here. This is from a textbook published by Routledge a while back now, but this is a really important paragraph which starts: isokinetic dynamometry is the assessment of dynamic muscle strength and function, in general, by measuring the joint moment exerted during constant joint angular velocity movements. It has widespread applications in sport, exercise and pathological conditions, for the measurement of muscle strength, for assessment of training or rehabilitation programs, the prediction of performance, the prevention of injuries, and... So let's just reflect a little bit on what Carl Payton is writing here in this paragraph. So if we start in terms of the basic principles of isokinetic dynamometry, it's what we'd expect. It's an assessment of strength, but it's about what's called joint moments. We'll explain what moments are as we go through, but fundamentally we're assessing angular displacement, angular velocities, a force produced across the range of motion. So fundamentally we're assessing, he's referred to joint moments, we can refer to this in the principles of what we're dealing with here as torque, rather than actually assessing force. It's related to the assessment of things like training and rehab, so we can use it to kind of monitor and evaluate athletes and clinical population groups and non-athletes alike. And it really gives us a much more defined exploration of muscle physiology under different loads and different angular velocities than we would see, for example, if we were just doing something like an isoinertial strength test. So what is the setup? Well, what you can see on the screen here, we can see in the insert, we can see a participant sitting. This is using a Cybex isokinetic dynamometer in one of our laboratories. And what you can see is you can see the participant on the dynamometer, and you can see we've got the leg in this example is in extension, and it looks like it's been isolated. You can just make out that it's kind of connected. There's an arm which extends from this section here. This is actually technically the dynamometer part here. So what it refers to is what we see on the main image here. So what we have is we have this control unit. So you've obviously got software which is powering the whole system. So we have the Cybex software here, and what it's doing, it sets angular velocities, and then it compares the angular velocity with the actual angular velocity. So let me explain what that means. So we want to assess the maximum amount of force in any movement. So we could prescribe, for example, in this image here, we're going to have our participant and ask them that we want to move them at a velocity, an angular velocity of 60 degrees per second. So the limb would move, in 1 second it would move through 60 degrees of range of motion. But what you have to remember is that in any movement, as the limb moves, it has to start from a zero angular velocity, and it will in essence go up to the range, the angular velocity we're after, which in this case is 60 degrees per second. So what happens is that the participant in this case, because we're going for knee flexion to extension, so let's assume we're doing that movement. We don't worry about the contraction at the moment, but in this example here, they're being asked to work at, say, 60 degrees per second, and as they're being asked to work at 60 degrees per second, the dynamometer arm will start to accelerate as they push. But we've preset the dynamometer that we want it to work at 60 degrees per second. So it will accelerate from 0 up to 60 degrees per second, and then it will hold at 60 degrees per second. So the limb will carry on moving throughout that range of motion. So what we then have is the participant pushing against the dynamometer, which is what this arrow here indicates. But as hard as they push against the dynamometer will apply a braking mechanism in this example in the opposite direction. So it's trying to slow the angular velocity. The angular velocity will still remain at 60 degrees per second, but it's in essence trying to match it. So we're matching on angular velocity once we get up to acceleration, and then the braking force that the dynamometer applies is matched to the force which is applied through the dynamometer arm. And that is the condition of being isokinetic. We have a constant, once we're at that speed, angular velocity, and then we have a continually recorded torque, because we're matching the torque being applied with a resistive braking movement on the dynamometer itself. And we can do this on any dynamometer, whether it's Cybex or alternate models. You can do this for any joint, any muscle contraction, and pretty much any speed. So you could do this eccentrically, concentrically, you could do it for abduction, adduction, internal, external rotations, you name it, you could actually do this. And what we are doing, which makes it very different to, for example, isoinertial testing, is we are isolating the muscles related to the movement around the joint. So in this example here, where we're going from knee flexion to extension through this range of motion here, as we're seeing on the larger image here, is we're clearly isolating the prime movers of the knee. So we're isolating the extensors and flexors of the knee, the quads and the hamstring group. It's nothing to do with any of the other muscles, and that's the one thing that differentiates isokinetic dynamometry from more conventional measures of strength. Is it is very much about isolating the joints that we're interested in, and therefore the muscles that are used to articulate that joint. So in the example we've got here, we can see we've got the device set up, as you'll see on the video in a moment here. And what we have is we have a series of comparisons taking place. The dynamometer arm will start to move. You'll see it in this example here. The dynamometer arm will start to move. It will accelerate. So it's going to read that velocity. It's going to compare that angular velocity to the preset angular velocity. It's going to compare the two. If the actual velocity is less than the target, it's going to decrease the braking moment. If it's greater, it will increase the braking moment. In other words, it's going to prevent you from basically accelerating too fast or decelerating too much by matching the force. So let's watch this in this video here. Okay, let's watch that again, and then we'll put an explanation over the top. So, we can see the participant has now gone from flexion to extension, and the dynamometer is being asked in this case to work at 60 degrees per second. And so as the limb is accelerating, it moves up to 60 degrees per second. It's almost impossible to see it, but you can see on the screen, you can see the force being produced, the torque being produced across the range of motion. So we'll watch it again. So it will accelerate very briefly at the onset of exercise. We get up to kind of the target speed, but the participant is always being asked to produce maximal force against the dynamometer, in this case both against flexion and extension. This is under concentric loading. And that's fundamentally the key to the way the dynamometer works. It's that idea that you apply maximal force throughout the range of motion, because you're trying to evaluate strength. So we need to know that they've applied the maximum amount of force. Now, if we think about kind of the length-tension relationship of the muscle, you can see the way that that changes throughout the range of motion. So what I want you to do this time is focus on the screen inside here. So look at the little screen, and you can see the force traces. And you'll notice that as the limb moves, that the trace has a peak towards the midpoint and it deteriorates at the two ends. It's representing our length-tension relationship of the muscle. So let's think about that perhaps in a slightly more simplistic way and explain about what happens when we change the muscle articulation, the muscle action. So here we've got two examples. We've got the black line here is going to represent for us the thigh muscle, and this is going to represent our knee joints, the articulation in both examples. We then have, in this example here, we have the tib and the fib, the tibula and the fibula, and then we have our foot. So this is kind of a participant, like we saw in the video, sat on the dynamometer. Now what we've gone from is we've gone from a position of flexion to a position of extension. So the limb has gone from around about 90-degree knee angle to around about almost horizontal in this kind of range of motion. So we've gone through this kind of range of motion that you can see here. In this scenario, the participant is applying the force. They're trying to push the dynamometer arm. So remember that the limb is going to be moving at a constant angular velocity. Well, you're going to push as hard as you can, and if you accelerate it too fast, the dynamometer will apply the resistance in the opposite direction to prevent you over accelerating, but you're working as hard as you can. So if we're pushing the dynamometer arm, so we're going from flexion to extension and we're pushing the arm, the dynamometer in this example is applying a resistance in the exact opposite direction. You're pushing, it's pushing back against you. In that scenario, that is referred to as concentric extension. So the limb has gone from flexion to extension. But remember that under concentric loading, we get a shortening of the muscle. And you'll see, perhaps when we show you this eccentrically, the absolute distinction in terms of the way this works. So if we look at scenario 2, in scenario 2, we're going from our position of flexion and we're going to extension, so exactly the same principle. But in this example, notice the way the forces are operating. So the limb, remember that the limb is going to move through this range of motion. And we've got a preset target of say 60 degrees per second, so the dynamometer will start to move. What is going to happen is that in this example, the participant is actually trying to prevent the limb from accelerating. They're trying to prevent it from moving through this range of motion. So they're pulling back against the dynamometer arm. The dynamometer is trying to pull in the opposite direction. It's trying to accelerate. So here, we're decelerating or trying to apply deceleration, therefore it is eccentric extension. In this example over here, we're trying to accelerate the dynamometer arm and it is therefore concentric. So it's really important to kind of get that distinction in terms of understanding the movements. So we can evaluate now, which is another differentiation to isoinertial loading, we can now evaluate the amount of torque being produced under concentric and eccentric loadings, which we cannot do when we work doing conventional isoinertial testing. But you can see the difference in terms of what is being required. In here, you're trying to accelerate the arm and the dynamometer will try and apply a braking force to slow you down. In this example here, you're trying to slow the dynamometer down, you're trying to apply the braking force, whereas the dynamometer is trying to accelerate the movement, and therefore we measure the force across that range of motion. Same scenario, but we're going to change the movement a little bit. Again, we're using the knee in our example, but this time we're going to start in extension. So we're going from extension to flexion. Okay, so extension to flexion. Now in this example, what's going to happen is that the limb is going to go back to flexion. The dynamometer is going to try and accelerate. You're going to try and resist it a little bit. You're pushing in the opposite direction. That is concentric flexion. In this example, we're going from extension to flexion, but this time you are trying to pull the dynamometer into flexion. The dynamometer is trying to prevent you from pulling into flexion, so it's applying the braking force this time, and therefore that is eccentric flexion. So it gives us this kind of differentiation between what we do under both extension and flexion, that we can isolate those, but also that we're able to isolate and separate out what is happening under both eccentric and concentric loading. So let's show you this, and what I want you to focus on, I'm going to show you the concentric first at 60 degrees per second. So it's the same as actually we've seen before, but just watch the movement and then we'll compare that to what happens at 60 degrees per second under eccentric. So you can see the force traces generating on the screen, and you can see the participant is accelerating, the dynamometer resisting. Now she's pulling back and the dynamometer is trying to do the opposite. So this is full concentric loading. Now, watch what happens when we go eccentrically. So it doesn't look noticeable, but she's now trying to resist the dynamometer arm. In this example, she's pulling it back. Now she's trying to prevent, she's trying to break it. The dynamometer arm is doing the opposite. So let's slow that down and we'll explain again to make this one clearer. So what we need to think about is when she's working, when she's going to work eccentrically, we're coming from extension to flexion. So when we're coming from extension to flexion, the participant is trying to accelerate, the dynamometer is trying to decelerate. Now when we go from flexion to extension, the participant is going to apply the deceleration, the braking force. The dynamometer arm is going to try and apply the acceleration force. And you can see a difference in the muscle action. So we've now got these kind of inverted curves that you can see on the screen here. So now what we'll do is we're going to try and play both of these simultaneously. And watch, remember these are across the same range of motion. Eccentric muscle actions are much harder to perform because you're asking the participant to apply a braking force. Under the concentric loading, it's a much more natural movement to undertake. It's really important to understand those differentiations a little bit. So remember, if we just go back, so we're just really clear. So if we go back, so here we've got concentric going into extension. Notice the way the forces are being applied. The participant is going to accelerate or try to accelerate. The dynamometer arm is going to try and decelerate. But fundamentally, we're going through this accelerational approach. When we go through eccentrically, the participant is trying to decelerate. The dynamometer arm is trying to accelerate. So understanding that kind of differentiation between the two. But when we then get into going from flexion to extension, notice the way the forces are being applied. In this example, the dynamometer arm is trying to accelerate the limb back to flexion. The participant is trying to put the braking force on. In this example here, the limb is falling. So the participant is going to apply the force to try and pull it back as quickly as possible. The dynamometer is going to pull in the opposite direction. So this becomes the braking force and therefore creates the muscle under that state of elongation.